Morning, everybody. I'll be your chair for this session. I think we're going to get started. I think these are all contributed talks for this session, so they'll all be 15 minutes with 5 minutes of questions. And with that, we'll start with Youngjin An, who's going to talk about optically induced phase transition and compressively strained bismuth ferrite on lanthanum aluminate.
Thank you for your introduction, and good morning, everyone. It's really a pleasure to present my research work in front of the distinguished people in the field and in DC, and thanks to organizer for this great workshop. And today I'm going to talk about the optically induced phase transition in bismuth ferrite on lanthanum aluminate substrate. And first, I would like to acknowledge the support from my advisor, Professor Paul Evans, and my group members and collaborators for the characterizations and the sample preparations. Dr. Wen and Dr. Xiaoyi from the Advanced Photon Source in Argonne National Lab, and Dr. Zhou from ESRF, European Synchrotron Radiation Facilities, and for the samples, the Dr. Zhengli Luo and Han Xu from the University of Science and Technology of China. And I appreciate the support from the US NSF and also DOE for the research work. And I would like to start my talk with the brief introduction to the background of this research work. So since the lots of interesting optical effects such as photogenerated current and the photorestrictions in ferroelectric and multiferroic system has been discovered, and lots of research work has been followed to understand the physical process in the effects. And also, it is expected to provide a new path to understand the fundamental physics in multiferroic and also the ferroelectric system, and also provide new method to control the functionalities of these materials. And I would like to focus on the photorestrictions more, and the photorestriction is defined by the optically induced deformations of the lattice. And it is very important because the structure of the ferroelectric and multiferroic systems are closely related to the functional properties. And also, it is well explained and understood with the mechanism optically induced changes in the internal field leading to the converse piezoelectricities. So I will explain a little about the mechanism. So ferroelectric and multiferroic systems have the polarization and internal field which have the opposite directions to each other. And when the light source excites the charge carrier, the charge carrier can redistribute the internal electric field. And in a result, the converse piezoelectricity or piezoelectric response initiate. And this is the source of the lattice distortion deformation by optical excitations. And lots of studies have been done to understand these effects, but the studies of the optical effect on the structure have been limited to only to the lattice. So I think more comprehensive study about the structural degree of freedom controllable with the optical excitation has to be performed. And they're going to provide more understanding of these effects and also provide more potential for future applications. So we set up the hypothesis based on the previous work in our group. And it is well known that bismuth ferrite can have the coexistence of the tetragonal-like phase, so it's T-like phase, and the rhombohedral-like phase, so R-like phase. In the system at the same time. And also, our group have demonstrated that the T-like phase and R-like phase can be transformed to each other by using the applied electric field. We use the X-ray diffractions to study the phase transition with the applied electric field, and also perform the density functional theory calculation showing that the piezoelectric expansion and contraction can change the energy of the free energy of the multiferric system. So we set up the hypothesis saying that if the converse piezoelectric response by optical excitation is the source of these lattice deformations, then optical excitation has to drive the structural phase transition too. And here's the question that I would like to answer throughout this presentation. The first question is can the structural phase transition be driven with optical excitation? And the second one is what strategy can be used to distinguish the thermal effects in the optically induced lattice deformation and also the structural transformations. I need to explain a little in depth about this one. Since we usually use the above band gap energy light source to excite the charge carrier, there is always the thermalization process because of the excess energy of the excited charge carrier, leading to heating to the sample. And it's extremely hard to separate the thermal effect because the thermal effect can lead to the lattice expansion, and also the optical effect can lead to the lattice expansions. So we use our own strategy, by using our bottom electrode as our thermometers, and I'll talk about this one later. And the last one is what are the effects of the local environment in a complex multi-phase system. So we already know that this bismuth ferrite have the multi-phase, and depending on the position of the system, the microstructure of the system will be different, and also that would cause the different local strain state. And we would like to test what is the effect of the local microstructures on the optically induced structural transformations. We performed the spatially resolved experiment to test this hypothesis and to answer these questions. And we used the in situ palm probe time resolved X-ray diffraction experiment in the beamline 7 at APS, Advanced Photon Source in Oregon National Laboratory. Since we already know the bismuth ferrite the strain in the bismuth ferrite thin film can be induced within few picoseconds. The time resolved measurement is essential to study structural transformation with optical excitations. So here is the experimental geometry that we use. And beamline 7 provide the laser system which is synchronized with the X-ray and allowing the time resolved measurement, and also provide the nano-sized X-ray spot, so we can do the spatially resolved measurement in beamline 7. We use the optical pulse of the 160 micrometer in size and also 50 femtoseconds time duration, and we use the 400 nanometer excitations. And we use the X-ray with the 400 nanometer in size and the energy of the 11 kilo electron volt. And here is the sample we use. We use the 70 nanometer thick bismuth ferrite epithelially deposit on the lanthanum strontium magnate electrode and on the lanthanum aluminate substrates. Because of this thickness can have the coexistence of the R-like phase and T-like phase at the same time, we can use this system to test our hypothesis. And this is the X-ray reciprocal space map involving the T-like phase reflection and R-like phase reflection. So we use these two reflections to test our hypothesis and measure the intensity and the wave vector of those two phase reflections. Here's the first result of our experiment. So it is a time-resolved structural transformation. We use, since the T-like phase reflection intensity and also the R-like phase reflection intensity are proportional to the fraction of the phases in the system, we can use the T-like phase intensity changes as a signal of the phase transition. So we plot here the T-like phase intensity changes as a function of time. And time 0 means the time when the 50 femtosecond time duration of the optical pulse is induced, and we see the saturations of the intensity at 1 nanosecond. Also, the refraction shifted to the lower wave vector, indicating the lattice expansions. And to systematically study, we have measured the intensity changes as a function of fluence and also lattice parameter, and compare with the electrically driven phase transitions. And what we have seen is the T-like phase intensity go up and R-like reflection intensity go down, which means the fraction of the T-like phase increase and fraction of the R-like phase decrease. And so it indicates that it's evidence that the R-like phase is transited to the T-like phase, and also see the linear expansion with increasing optical fluence. But the thing is, electrically driven phase transition show this 10% of changes and 0.15% of strain, which is much less than what we have observed in the optical excitations. So we have seen the 0.34% of the strain for the 10% of the intensity changes. If the converse piezoelectric effect or response is the source of this phase transition, we think that this strain should be the same. So we set up the hypothesis that the additional lattice expansion arises from the thermalization process. So we test this one by using the lengthened LSMO electrode on bottom of the bismuth ferrite thin film. So we have seen the strain in the LSMO, and we think this is arrived from the heat diffusion from bismuth ferrite, because based on the calculation of with the optical parameter of the bismuth ferrite and the LSMO, the absorbed fluence has to be less than 3% of the incident fluence, which means that the effect of the fluence on the LSMO has to be negligible. So we think this strain arrives from the heat diffusions, and we convert this strain to the temperature increase, and by using the heat from this temperature increase, we estimate the heat in the bismuth ferrite by doing the heat diffusion analysis. And we got the thermally induced strain here, indicated by the red line, and got the how much piezoelectric response can be induced with the experimentally determined strain. And it was 0.18%, which is quite close to the electrically driven strain. So we conclude that the similar magnitude of the structural transformation is necessary to see the phase transitions, which is electrically driven. And because we now know that the temperature increase arises in the bismuth ferrite, we need to measure the intensity changes by temperature, and we did with our laboratory, and see that the intensity changes should be less than 5%, and we see the T-like phase and R-like phase intensity both decrease, so it cannot explain the intensity changes observed in the optical excitation case. So we conclude that this intensity changes arise from the phase transition between T-like phase and R-like phase. Finally, we have performed the spatially resolved measurement to see how the microstructure of the bismuth ferrite affect the structural transformation. So we use the 400 nanometer X-ray and measure the R-like phase intensity distributions, and show that this stripe pattern and indicating the microstructure is not homogeneous throughout the measured regions. And we measured the strain and intensity changes within the region indicated by the red dotted boxes, and see the strain variation is quite uniform, but the intensity changes of T-like phase significantly varied depending on the position of the sample. We can run two things from this result. One is the structural phase transition is not solely explained with the strain, and also there should be another factor contributing to phase transition. And another thing we can run is the strain variation was the uniform. So strain, optically induced strain is only a function of the number of charge carriers. And we did the full field X-ray microscope and also sub-micron X-ray diffraction mapping to study a microstructure of the system and see these stripe patterns in the T-like phase and the inhomogeneous intensity distribution R-like phase. But we think that this means that the local microstructure will be different and also local strain state. But because of limited resolution of the X-ray, we cannot exactly resolve the exact origin of these different structure, different degree of the structure transformations. And here's my conclusions, and thanks for your attention. I will take the questions.
Do you have any questions?
Before others will find a question to the topic, sorry, nice subject. There's some difficulty. Professor Salier yesterday evening have troubles to reach the hotel, and someone from the conference helped him. Is he here in the audience, the person? We would need to his help. No, otherwise, because there was some lost luggage on the way. Yeah, it's not the case.
Go back to the page with the X-ray mapping.
Yeah. This one?
No, the X-ray mapping. The next.
Yes.
Yeah. So on the scale bar, I read 30 micrometer. Is this on the film?
You mean this one?
Yeah. It shows 30 micrometer.
Yeah, it's from the film.
So the film, what you see, those contrasts, are they on the scale of like 5 micron or 10 micron? Are they domains or something else?
I think we believe that this arises from the twin structure of the lanthanum aluminate substrate. So we deposit our bismuth ferrite on this twin structure of the lanthanum aluminate. So this feature is arises from that because it has different tilting. Because of that, we get the different intensity from that.
Okay. Also, that's from the substrate. This contrast.
Yeah, we're pretty sure about that.
Okay, so you think you have enough resolution to probe the film or not? I guess it's not, right?
It's not.
Okay, all right, thank you.
So do you know the amount of expansion of the lattice when you irradiate?
Yes. It depends on the... oh my God, sorry.
Because that itself could drive the transition.
Yeah, we're pretty sure about that because we tried the electrically driven one and also the optical excitation and measured this amount of the lattice expansion happens. And for the electrically driven, this amount of the lattice expansion happen and drive the 10% of the phase transitions and also the 10% of the phase transition because there is a big discrepancy which is arised by the thermal effect.
Any further questions? No, with that, let's thank the speaker again.
Thank you.
And go ahead. Yeah, I'll give you 5 minutes and I'll give you 1 minute.
Okay, good morning, everybody. So it's another great workshop. What I'm going to show you today is it's a bit more unusual for what we do, and it's more technological, despite the fact that we're in a fundamental physics workshop. So I hope you'll like it. I come from the French Atomic Energy Authority, CA, in Saclay, near Paris. And I'm going to talk to you about interface chemistry between an electrode and a technological layer of PZT. In past workshops, we've shown quite a lot of work using electron spectroscopy and combining it with spatial resolution to image electron emission from surfaces and to image in particular domain structures, domain walls in ferroelectrics, ferroelastics. Here we sacrificed the spatial resolution, and instead, thanks to tuning the photon energy that we're going to be using to carrying out our electron spectroscopy, we're obtaining depth resolution. And this allows us to look at surfaces, and it will allow us to look also at interfaces buried beneath, several tens of nanometers beneath the surface. So the object, the material in question, is PZT, it's a morphotropic phase boundary. Why do we do this? It's so indicated, or it might be indicated if I could get it to work here. Surface-mounted devices take up a large area on PCBs. If you replace them with integrated passive devices, much smaller footprint, but to get the same performance, you need to increase, for example, the capacitance density. And the solution for doing this is twofold. On the one hand, you can change the materials, and that's what we do here. You can use a high dielectric material, such as PZT, and then there's an architecture-based solution, 3D multi-beam metal insulator metal, which is indicated here. So we're combining the high dielectric constant expected from PZT with favorable architecture. Now, it's not that simple, obviously, and in particular, the role of the interface is very important. Are the electrodes that you use, do they provide sufficient screening to stabilize the ferroelectric state, or is there a remnant internal field? If the electrodes are asymmetric, are the bands skewed, changing the band structure of the capacitor? Do electrons spill over from the electrode into the dielectric, basically meaning that you're metallizing a thin layer, or at least creating an altered thin layer? Is there a specific interface chemistry? And then other questions such as adhesion. Adhesion is illustrated here. A favorite electrode on seamless-compatible capacitors would be, could be platinum. But when you use platinum, in fact, that delaminates after a certain number of cycles. And so the solution is platinum with a thin ruthenium layer between the platinum and the PZT. And there's no delamination, and that's something we're working on quite recently. Another problem with PZT, of course, is that it's volatile. There's a whole lot of annealing steps to be taken during processing, and so you lose lead. To compensate, the solution is quite simple. You just increase the lead content in the precursors. Well, if you increase lead content in the precursors, then maybe you're changing the stoichiometry, and maybe you're changing the dielectric constant. So there's quite a lot of optimization to be done before you can use this material in realistic devices. So here are the samples. It's industry-ready processing, wet chemistry, sol gel. There are basically 4 layers. Each layer is about 50 nanometers thick. And these were made with varying lead precursor excess. In fact, this is what the sample looks like. It's a standard silicon wafer. It comes from ST Microelectronics. Adhesion layer, bottom electrode. And then we use different seed layers with different lead excesses, 10, 15, 20, 30%, and the last layer as well has the same lead excess. There's several annealing steps, drying, pyrolysis, and then rapid thermal annealing to show the crystallization and therefore the ferroelectric properties. Technique we're using, photoelectron spectroscopy, is photon in, electron out. This is what we want to know. The valence band, the core levels with the chemical signature, valence states, so on and so forth. This is what we measure. It's a spectrum which looks like this, or a spectrum which looks like this, and as a function of the kinetic energy with the core levels. And knowing the work function, knowing the incident photon energy, we hope to be able to deduce the initial states of the electronic structure and the valence structure. Very important is that this is essentially a surface-sensitive technique. Here is the energy, the kinetic energy of the photoelectrons, and this is the inelastic mean-free path distance traveled before undergoing some kind of inelastic collision and therefore losing energy. And it's round about a nanometer for typical electron energies. So we're looking essentially most of the time at the surface of our samples. some SEM characterization as a function of the lead content. At low lead excess in the precursor, lots of nanostructures. These are about 10 nanometers to 15 nanometers in diameter, average, quite dense, covering about a fifth of the surface. They get less dense here, they increase in size, they almost disappear when there's 20% in there, they completely disappear, and the grain size of the PZT is much, much bigger. So there is a clear effect of the lead precursor. You can see this in the XPS. The lead core levels don't change. That means that the lead chemical state and local environment is always the same, whatever the lead excess level we use. However, this is not the case for the zirconium. For the 10%, there are clearly two environments. One is that associated with PZT, and the other one is at higher energy. And as we're going to see, it's actually it is associated with these nanostructures, which are more like zirconium oxide. This second component decreases with increasing lead precursor excess, and effectively at 30%, there is no more nanostructures, and this second high binding energy component has disappeared. Looking in more detail at the 10% sample, this is done as a function of takeoff angle, so we actually go to more glancing emission here, and the second high energy component has increased, confirming that its surface nature, so it's correlated with these nanostructures. We've then sputtered the surface, and this second component disappears. So once again, we've removed matter from the surface. This corresponds to those nanostructures. And finally, the oxygen 1s, when we go to more glancing emission, again, this second component, which is related to that surface phase, surface nanostructures, has increased in intensity. So we can do some quantitative analysis, and basically what we have is a discontinuous surface layer of 15 nanometer diameter ZrO 1.89 nanostructures, almost ZrO2. Final information on the film before putting down the electrodes. X-ray diffraction. In fact, the lead excess can also change the preferred orientation of the sol gel layers. That can be quite important for the absolute value of the polarization you obtain. And this is glancing angle X-ray diffraction. In other words, very sensitive to 30-40 angstroms, 3 or 4 nanometers on both the PZT-10, the PZT-30. PZT-30, nothing really to report. All the expected peaks are there. PZT-10, confirmation of the crystallographic structure of these that surface phase, the nanostructures. We have peaks corresponding to ZrO2. So we're pretty confident of the chemical nature of that layer. Now we grow the electrode, our ruthenium platinum electrode. Here we have cross-sectional TEM, and what we see is that these nanostructures have been preserved. There they are. So the electrode actually follows that topography. You look at some energy loss. It confirms the chemical nature of them, as observed in XPS. There's zirconium and oxygen. And what we also see in the electrode characterization is there's a strong offset, there's a strong imprint, there's an internal field there after deposition. Other electrical results on these capacitors now as a function of the lead excess. First of all, the capacitance density, if you use surface area, actually increases with increasing lead excess. So this is quite important. It's 10%. It's quite significant. The loss tangent decreases, which is good as well if you want some high-performance devices with lower power consumption. But unfortunately, the breakdown field actually decreases with increasing lead excess. And the decrease is quite important. It goes from 1.6 to 1.3. If we use a simple two-layer, a very simple two-layer capacitor model, the only assumption here is the dielectric constant of these nanostructures of ZrO2, so we assume 25. And what we would expect then is that the device made with PZT-10 would be about 0.86, have the capacitance of 0.86 of the device made with PZT-30, which essentially is what we see. So it's far better than an order of magnitude agreement. The decrease in the breakdown field, what we suggest, to be confirmed, but what we suggest is that it's due to the band gap of ZrO2, which is about 5.8 eV. It's about almost twice that of PZT. And so this creates a barrier. This creates a more efficient barrier to breakdown and therefore improves the performance. So we can see that there are contradictory tendencies here as you increase the excess, and technologists, they have to choose where is the optimum value for the lead precursor. Now we want to look at the chemistry of this interface, and we do this with what's called HAXPES, which is hard X-ray photoelectron spectroscopy. Standard X-ray photoelectron spectroscopy, as I showed you on the surface, allows you to look at the first nanometer or so of the chemistry and the electronic structure. And this is because of the inelastic mean-free path. Now, if you do the same analysis on the same levels, but using much harder X-rays, for us, hard X-rays are several kilovolts, not the tens of kilovolts in the SRF or in argon, as the last speaker showed us, then what we get is this. The inelastic mean-free path goes up to about 10 nanometers, and basically that means you're getting information from the first 25, 30 nanometers. So you can see through a top electrode, a realistic top electrode, not some ultra-thin thing, which is discontinuous and is probably not even a real metal, but something like 10 nanometers. It's reasonable, it's continuous, it's going to screen as a technological electrode would actually do, and you can look at this interface, providing that there is a distinctive chemical signature coming from that interface. So that's what was done. The experiments were done at the Slurry Synchrotron Galaxy's beamline. This is do-it-yourself operando. Do-it-yourself because this is what the sample holder looked like. Okay, so there's bits of copper to ensure the two contacts. It's about the same size as a 10-cent piece. We've glued the thing onto some circuit board, but it worked. In our case, the bottom electrode is grounded, and we're biasing the top electrode. And this allows us not just to probe that buried interface, but also to get the response, the signature, chemical and electronic signature, under bias. In other words, under real operating conditions. So here's the first results. This is a reference spectrum without the top electrode. All the usual core level peaks are there. We put the top electrode down, and then effectively, on this scale anyway, we've almost completely attenuated the signal coming from the PZT. This is just to underline the need for probing down below that electrode and using hard X-rays. Here are the raw data. The two bias states we used were +3 and -7. That was because you remember the electrode characteristic, there was an offset. There was a 2-volt offset. So these values are actually symmetric around that measured butterfly loop. So the spectra are offset by 10 volts. If you correct for that, then of course the electrode core levels coincide, but you can see here there are residual differences in the emission coming from the PZT. And these residual differences are therefore due to the polarization state affecting the PZT near the interface. These are the results. This, again, is the reference without the electrode. That's why the statistics are much better. Here's a bit noisier. We can see three things. First of all, this is the component due to the zirconium. It includes both the nanostructures and the zirconium in the first layers of the PZT. And these are the components due to the lead. What we see is that as the bias changes, the whole spectrum is shifted. Remember, we've corrected for the applied bias. So this is polarization due to internal field in the PZT. Secondly, there is this additional peak. It's a singlet. Therefore, it must be related to the zirconium 3s. It can't be related to the lead. And this exists also for all biases. So what we know is that these nanostructures are present at the interface, that as the bias changes, there is a polarization-induced shift in the electronic levels at the interface, and there is some specific interface chemistry. So I'll conclude there. Just to remind you, we looked at the sol-gel PZT layers. There is, depending on the lead excess, we have there can be a low dielectric layer based on zirconium oxide. This layer reduces the capacitance density and loss tangent, but it improves the loss tangent, but it reduces also the breakdown voltage. There's a specific interface chemistry. The screening, despite the solid electrode, is imperfect, and this gives rise to an internal field. There's one thing we haven't in these technological samples considered, is that the solid gel is grown thick layer by thick layer, and we haven't considered what happens at the interface between these layers, which is probably an important point. So that's about it. These are the people who did the work. Ibrahim Aghe was the guy who did his thesis on this, and he's just graduated. And just to reassure you, or to reassure me maybe, I hope next time we'll be able to report some nice data on domain walls in a completely different systems, calcium titanate. Here we have the electron image, here we have the AFM, we can look at angles, and we can look at polarity in the walls. So we'll go back to that, I hope, next year. Thank you.
Questions? Microphone.
Thank you for the talk. Can you quantify the magnitude of the internal field as a function of the polarization?
Yes, I can't.
What does happen if you change the polarization, for instance?
Yeah, I mean, we can. It's quite simple to do. We just look at the offset. I can't give you the figure there. I can't remember the figure. But yes, we can. We can indeed. I'll show you that afterwards if you want.
Yeah, come on up.
I understood. Nice talk. Thank you for doing these measurements on those nanoparticles that the community has often thought it's pyrochlor.
Yeah.
One quick question. When you look at the orientation of the films, if I understood correctly, you seem to suggest that when you do not have enough excess lead, you do get a 100 orientation. This seems to be somewhat contrary to a lot of other literature reports in which when there is higher excess lead, you do get more oriented films because the lead oxide excess is a sheet layer and therefore allows a 001 orientation. Can you comment on that?
We've seen this it's reproducible first of all, so it's a real result. But it may be to do with the exact temperatures we've used for the crystallization. We do 2 rapid thermal annealings, one after the first layer, which is the seed layer, the PZT, and one that. And as you know, because of the crystallization temperatures, there's a strong gradient between the titanium and the zirconium in each layer. So what goes down first is titanium-rich. The titanium-rich, so you at the bottom of your layer, you will have PTO, or almost PTO. So in fact, what we're looking at is in that seed layer is the growth of PTO on platinum, rather than PZT. So this may have something to do with it.
Quite want to talk later.
Yeah.
Thank you.
Come on up. And can we have the next speaker come up too, please?
Tell us a little bit about your sol gel. Did you make that sol gel? Can you tell us the basis of it? Or was it commercially acquired?
It's I did not make it. It was done in clean rooms in the CEA in Grenoble. The solutions, I think, were bought from Japan. They have a standard. I can give you a bit more detail in the papers.
All right, thanks.
Yeah.
Okay, with that, we'll thank the speaker again. Thanks. So our next speaker is going to talk about insights into ferroelectricity with hafnium zirconate thin films, a new ferroelectric phase.
Good morning. Thank you for the introduction. My name is Pawan. I come from SPMS lab at Centrale Supélec in Paris. I work with Brahim, who's here in the audience. And this work, in fact, it's a pleasure to be speaking in front of such a distinguished audience, and I thank the organizers for this opportunity. This work is, in fact, a collaboration between our own lab, Beatrice Noida's lab at the University of Groningen. Yingfen is a student who is actively involved in this. And Jorge and Edje from Luxembourg Institute of Science and Technology doing a lot of computation for this. And of course, Philip and Sylvia, who do a lot of nanofabrication to make devices for this work. And both of them are also from C2N in Paris. So let's get started. First things first, why study ferroelectricity in Hafnia? And I don't think we have, I need to motivate this crowd here, but I'll anyway do it. From the perspective of everyday electronic devices have like billions of transistors in them, and these transistors switch from an off state to an on state. And ideally, you would like a transistor characteristic to be something like this, where shown in the red, where in the off state you have zero current, and in the on state you have some finite current, and the switching happens very sharp. But ideality is not reality, and in reality we have MOSFETs which kind of leisurely go up from the off state to on state. The slope of switching is what is characterized by subthreshold slope or subthreshold swing. And that is given by this expression. And if you look at this expression, we see that just for conventional metal oxides, this number cannot be made less than 60 millivolt per decade, because this 1 plus some positive number is always less than 1. Is always greater than 1. So the idea, and so if you operate these transistors just below the threshold voltage and above the threshold voltage, in the off state you do have some leakage current. And so when we have devices in off state, they are leaking. So there is power loss for devices in the off state. And if we look at how the gate, and this is the so-called subthreshold leakage, and the power losses because of this subthreshold leakage actually intensify as the gate length decreases, as we keep miniaturizing devices. So this is bad, but fortunately we have a solution for that, which is try to make this quantity negative, use a negative capacitance as a gate oxide, and it's well known. So instead of MOSFET, we'll be using ferroelectric FET or a negative capacitance FET, and negative capacitance has been demonstrated in these ferroelectric materials by several groups in the recent past. So what's the delay? Why not use ferroelectrics already in microelectronic ferroelectric FETs? The problem is a well-known silicon compatibility issue with well-known ferroelectrics such as PZT and SPT. And furthermore, as you scale the gate stacks down, these ferroelectric materials, they lose their ferroelectricity because of depolarization fields. So a solution to this is perhaps to have let's call it a magic material, which has a robust nanoferroelectricity and which is also silicon compatible. And does that material exist? Yes, of course. There is Hafnia, and it has been discovered, ferroelectricity in Hafnia-based materials has been discovered in 2011 by this group in Dresden. So a quick introduction to basic structural details about Hafnia, and which is very isostructural with zirconia, because hafnium and zirconium have almost the same size for a given coordination and charge. So hafnia exists in the bulk phase, exists in this bulk monoclinic phase, where hafnium is coordinated with 7, has a coordination number of 7, so surrounded by 7 oxygens in such a polyhedron. And the more well-known phase is the T phase, which is the high temperature phase and high pressure phase. However, this T phase could be stabilized by doping hafnium or zirconium with yttrium, magnesium, and these yttria stabilized zirconia, magnesia stabilized zirconia are like blockbuster materials for solid ion conductors. So these are very well studied. However, the problem with these two phases is both of them are nonpolar. So both of them are useless for ferroelectric applications. The saving grace is the existence of an orthorhombic phase. And this is what is reported to be ferroelectric, or what is assumed to be ferroelectric in most of the recent works in hafnia-based materials, ferroelectricity. So this phase was first reported in 1990s in zirconia. as a bridge phase between the M and the T phases, but during the phase transformation, but there are no ferroelectric measurements until 2011. So since 2011, in fact, now it's a joke that you take any hafnia, any crystalline hafnia below 10 nanometers or something, it would become, and dope it with anything, it would become ferroelectric. So there have been several demonstrations based on different techniques and with different dopants. Insights, as always, come from theory as to what stabilizes this polar orthorhombic phase. And here, for instance, in this paper from in this paper from Munich, we have they consider surface energy of these small nanoparticles to be a stabilizing factor for this polar orthorhombic phase, and then they in fact determine the, for example, this red curve gives the energy stability of the ferroelectric phase, and it is stable in certain, say, size ranges depending on the composition of the material that they're looking at. Similarly, this group from University of Connecticut, they have applied. They suggest that while going, you could go to a polar orthorhombic phase by applying biaxial compression as well as electric field. So it looks like there are many pathways to get to this ferroelectric phase. However, the problem is that most of these films are polycrystalline, polyphase, so it's difficult to decouple individual effects experimentally and understand what the effect of each factor is on the ferroelectric, on stabilization of ferroelectric phases. So our strategy has been to, ideally, to design clean experiments where we study the effect of strain by changing the substrates. We study the effect of doping, specifically by choosing the hafnia-zirconia system, because zirconium has the same exact size as hafnium. So putting in zirconium in hafnium positions doesn't induce any internal strains, unlike, say, yttrium or lanthanum or some other ions. And also, we can study the effect of point defects by varying, in this experimental setup, by varying the oxygen partial pressure, for example. But what I'll show you in this talk is just one substrate, which is STO with LSMO as a back electrode, one composition, which is 50-50 of hafnium and zirconium, and the conditions optimized for growth of these films. So the stack looks something like this. It looks nice. But if you have a keen eyesight, you could recognize that at the interface of LSMO and SZO, something strange is happening, or something weird is going on. We will come back to this. But however, when you put another symmetric electrode and then measure the polarization electric field hysteresis, you do PV hysteresis, you do in fact see that for films which are thinner, 5 nanometer films, we measure a higher saturation polarization of around 35 microcoulomb per centimeter square compared to the thicker films. So this is true. Thinner it gets, the smaller the size gets, the better is the PV hysteresis. So there is some new kind of ferroelectricity, or different from what happens in conventional materials. And so to understand that, we did structural characterization using both XRD as well as electron microscopy. So here I show a theta to theta XRD plots. As a function of the film thickness. So this is a busy graph, but I want you to note a couple of things. One is the literature value of the orthorhombic 111 is here. Whereas what we see in films which are boxed here, they are the ferroelectric films. The rest of them are not ferroelectric. So beyond this thickness, it is not ferroelectric. Is a lattice parameter which is larger than what is reported in literature, and also larger than what is in the in thicker films. So our ferroelectric films seem to have a longer out-of-plane parameter, which could be coming because of compression in plane. Okay, so you can do some pole figure analysis around this 111 peak, and then see that this corresponds to a domain structure. So of 4 different domains, which are rotated 90 degrees with respect to each other. Plane view TEM also says the exact same thing, TEM diffraction. So I circle spots here in yellow, coming from 2 sets of domains, and in blue coming from two other sets of domains. And also we see a clear orientational relationship between the substrate and the film. Okay, so very quickly, because I don't have much time now, we do also cross-sectional stem measurements along by making cross-sections. So this is the plan view along this direction, along along several directions to get insights into what's happening. In thinner films, we do see a domain structure. Here I'm showing 180-degree domains. And in thicker films, we in fact see the evolution of not just 111 out of plane, but domains with 001, which is out of plane. And this is perhaps the reason why the polarization of this is less than the polarization of thinner films. So if we calculate what the d-spacings are, the d-spacings of 111 is different from 11-1, and this suggests, this is indicative of the fact that we don't have conventionally reported polar orthorhombic phase. In orthorhombic phase, these are supposed to be the same things. Same thing if you analyze the 001 domain, you do find some spots which are forbidden in a PCA to an orthorhombic phase. What phase is this? To do that, you go to the synchrotron, go back to this pole figure, analyze, let's say, all these spots, theta 2 theta scans around these spots. And here let's concentrate on one particular domain. Here we clearly see that there is a 3-to-1 multiplicity for the 111 peaks. And this is a clear indication that what we have is a rhombohedral phase, which has not been reported, which has been reported, but not in the context of ferroelectricity, and which is what excited our theorist, Jorge. So he did find a couple of rhombohedral polymorphs, which can be stabilized under strain using first principles calculations. And the polarizations of the more stable phases are like 15 microcoulomb per centimeter square. Actually less than what we measure experimentally. So this is one of the cases where theory is predicting lower numbers than what we are seeing experimentally. Okay, so as you keep increasing the thickness, this picture shows a gradual evolution to the M phase. Okay, so finally, let me talk about the interface. So the interface, these are the chemical maps, and we see that at the interface, we have a different phase of HZO itself, interface between LSMO and HZO. We have a different phase of HZO itself, and that is in fact a tetragonal phase, a T phase, which grows in the 001 direction, but it is completely epitaxially strained with respect to the substrate. So there is an 8% tensile strain T phase, which extends for 2 to 3 monolayers. Okay, so, and this is, so, okay, what is happening, right? So we do have LSMO STO. So here I'll show a very hand-waving cartoon. So I will select an in-plane parameter, which is convenient for me. So this is the 110 in-plane parameter of the LSMO STO, on which we grow a T phase. Initially, a T phase is formed for 2 to 3 monolayers, after which the system wants to relax strain. So once it relaxes, once there is strain relaxation, the next material or the incoming material should have a lesser in-plane parameter compared to this strained T phase. But there is a substrate constraint. So the way the system accommodates this is by rotating the crystals from 001 to 111. And when you rotate it, you still have a higher, say, relevant parameter. So what we need to do now is to apply compression, some kind of compression. And in fact, this is well known in the literature of zirconia. And what happens in PLD, for instance, is there is in situ crystallization, so we have the formation of nanoparticles. That is one source of compression or compressive stress. And then the second one is the substrate constraint. So using these two, we actually compress this cubic or tetragonal phase into a rhombohedral phase. what we have is is an R phase with a polarization, which is along a well-oriented R phase with a polarization which is out of plane. Okay, so the strain is accommodated by polar rhombohedral phase and domain formation, which is a standard trick to accommodate strain. And finally, this is me being patriotic. I come from India. In fact, this is the only flag where there's a wheel, which can be used to rotate crystals. And if you look at this, he's actually pointing out the direction of polarization. Okay, so I just want to point out that we submitted this paper recently, but it's available on arXiv. So if you're interested, you can take a look at this. Thank you very much.
We have time for some questions.
Just a comment to add in onto this. Another reason for using hafnium, of course, is that any sort of memory device based on ferroelectric hafnium dioxide will have write speeds which are orders of magnitude better than, for example, flash memories. And of course, there's very low power consumption. And then, as you said, I mean, this is really a con, but the important point is that this is CMOS compatible. Yeah. So that it can go into production lines. There's no major issue on pollution, on contamination, whatever. It's proven.
Sure,
so
sure.
Industry is interested.
So I was just taking one motivation, which is the FETs, but of course there is memory application. Sure, I agree with your comments.
Something known about critical temperature in such film?
Not in our work, but yes, it is known to be around 450 degrees Celsius or something.
Did you have to cycle the films to see the wake-up effect?
No, that's one advantage that I didn't mention here. In ALD-grown films, etc., which are in a different phase, clearly, you have to cycle it. I showed you that curve where you have to apply electric field and then biaxial
so these
strain.
were virgin.
These are as prepared ferroelectric. You don't have to cycle anything.
Anything else? So I have a question. Sorry, go ahead.
At 400 degrees Celsius, it would be paraelectric phase. Do you know the symmetry?
It's assumed to be monoclinic, P21 by C. But I mean, I don't know. So, not from our work, but others reported. You had a question?
Yeah, so I was curious as to whether or not you have any sort of in situ characterization during your PLD growth, and kind of, you have this changing of symmetry layer by layer. And
we have read, but we don't really see it because I think the lattice parameters are kind of similar.
Oh, but it's a big rotation, right?
Oh, when it rotates. Okay, so I didn't do the growth, so I should.
Okay.
That's a good question.
Might be interesting to see whether it's templating out as the tetragonal phase or if it's forming after the fact.
Yeah, that's a good question. Thank you.
Anything else? Okay, we'll have the next speaker come up. Our next speaker is Javier Junquera, who's going to talk about second principle simulations of counter-rotating vortice pairs in lead titanate, strontium titanate superlattices.
I am able to find where to plug it. Here, I found it. Okay. Working. Thank you. So, can you hear me? Okay, thank you very much, Mr. Chairman, and thanks to all of you and the organizers for giving me the opportunity to present here our results on second principle simulations of counter-rotating vortices pairs in lead titanate, strontium titanate superlattices. So first of all, I would like to thank my collaborators, Pablo García Fernández and Fernando Gómez at the University of Cantabria in Spain, Jorge Íñiguez, and our research student, Mauro Gonçalves, at the Luxembourg Institute of Science and Technology, Pablo Aguado Puente, who is now at the Queen's University at Belfast, and of course all the experimental help carried out by the group of Professor Rames and Elaine Martin at UC Berkeley. So one of the most important topics of this conference has been the domain walls. Domain walls are a very common understood object in the Ferroid community, but it's not the only way how a spatially changing order parameter can arrange. Especially in the last few years, and coming from the ferromagnet community, there are more complex patterns for this order parameter where they can be arranged in skyrmion, merons, antimerons, etc. So which kind of ferroelectric nanostructure develops depends critically on the relative magnitude of different energies that may involve magnetic anisotropy, spin-orbit interactions, exchange, presence of surfaces, interfaces, etc. So the question is, if in the magnet community, in the ferromagnets, we have all this rich behavior, can we do the same if we replace the spin degree of freedom by the electric dipole? So that's one of the main topics of this talk. So in this particular sense, lead titanate, strontium titanate superlattices is a very sensible material to look at. This is a fascinating material. Whatever you do in this system is interesting. The reason for this is that the very close competition between different orders here. So if we look at the bulk level, at the lead titanate, there are two phases that compete. One of them, two distortions. One of them is the ferroelectric distortion at gamma, and the other is the anti-ferrodistortive distortion. So at the bulk level, the ferroelectric distortion wins and inhibits the appearance of the second. Regarding strontium titanate, it's a quantum paraelectric and undergoes an anti-ferrodistortive phase transition at 105 Kelvin. When you put the two materials together in a superlattice, some of the symmetries are broken, and this very delicate balance between all of these order parameters may change. And completely new phases that do not appear at the bulk level may arise in these superlattices. Make predictions on this material is difficult because of several reasons. The first is the large spatial extension of the new phases, and the other is that the results are extremely sensitive to some external perturbations, such as the temperature, the periodicity of the superlattices, the electric field, the strain imposed by a given substrate, etc. So this, just the interplace of all these players here. Do I have a pointer? Mine is not. Okay, here it is. So the interplace of all of these may produce the appearance of phase competitions, order parameter coexistence, the emergence of new order topological parameters, and all of these effects can be found in these lead titanate, strontium titanate superlattices. So just an example about how the electrostatic coupling can be changed with the periodicity of the superlattices. So if we combine a ferroelectric and a dielectric material in one of these superlattices, any discontinuity in the out-of-plane component of the polarization at the interface between the ferroelectric and the dielectric may yield very large depolarizing fields that are energetically very costly. So if one way to just get rid of this penalty, electrostatic energy penalty, is that if we have a thin enough periodicity in the lead titanate, strontium titanate superlattices, the system may adopt a uniform polarization structure where here the out-of-plane component of the polarization is constant throughout the structure. So in this particular case, the ferroelectric layers are electrostatically coupled, and the price to pay for this is that we have to polarize the dielectric layer and somehow to reduce a little bit the polarization in the lead titanate. However, if we start to increase the number of layers of the dielectric, the energy that you have to pay to polarize strontium titanate increases, and at some point, you cannot afford it. And in that particular case, the system has to choose between revert to a paraelectric phase or just break in domains that are confined in the ferroelectric region that are now electrostatically decoupled. But these electrostatic degrees of freedom are not the only thing that are important in this system, because they are also prone to have a polarization rotation imposed by the in-plane lattice constant of the substrate. In particular, a compressive strain favors a 001 polarization, the so-called C phase, while a tensile strain favors an 110 polarization, the so-called AA phase, and in the middle, and very interestingly, in regions very close to the lattice constant of strontium titanate, there is a continuous phase transition, a continuous rotation between the C phase and the AA phase. So there is some tendency for the polarization to rotate. So a few years ago, we started to do some first principle calculations in this kind of lead titanate, strontium titanate superlattices, and essentially we were able to corroborate all these arguments. In particular, for a periodicity of 3 unit cells of lead titanate and 3 unit cells of strontium titanate, the ground state was monodomain, with the polarization pointing in this R phase, essentially along the 111 direction, while the domain structure here, we were able to stabilize the domain structure only as metastable phases. However, if we increase the number of unit cells from 3 to 6, then the domain structure becomes the most stable one, and they adopt here the shape of one of these domains of closure. So when the polarization goes from up to down, there is a continuous rotation of the polarization around 3 unit cells around the domain walls here. So this rotational pattern has been recently detected experimentally in this very nice image obtained using aberration-corrected transmission electron microscopy by the group of Rames, where these the so-called polar vortices are characterized here but as spontaneous formation of laterally alternating clockwise and counterclockwise vortices of electric polarization. So these vortices are made bichiral, and that was one of the most important questions that we asked. So are they chiral and therefore optically active or not? The point is that we are at the limit of the things that we can do from first principles. In particular, this calculation here for 3 unit cells of lead titanate, 3 unit cells of strontium titanate, and 16 unit cells of periodicity for the domain includes of the order of 1,000 atoms, and it took more than 6 months to relax. Single shot. So we cannot explore this kind of configurations in an easy way, and somehow we were forced to implement a new simulation method that we call second principles, and is already implemented in a code called Scale-Up. So what is the main goal of this second principle? So the goal is quite ambitious. So we want to simulate very large systems over 10 to the 4, 10 to the 5 atoms, including both the atomic and the electronic degrees of freedom, with an arbitrary high accuracy. Asymptotically, our accuracy is density functional theory. So everything at a modest computational cost and at operating conditions. That means at finite temperature, including time-dependent electric fields, defects, and so on and so forth. So this has been implemented in this code here. This is the web page if you want more information. So just a bird's eye overview of the method. We are combining an accurate model potential to describe the lattice dynamics, and we include here all the possible modes of the materials, ferroelectric, antiferrodistortive, whatever, all of them. And on top of that, we have a tight binding-like approach to describe the relevant electronic degrees of freedom, and we have the cross-talking between the lattice degrees of freedom and the electronic degrees of freedom. So we have all kind of electron phonon interactions. So we call it second principles because we don't have any input from the experiment. So all the parameters are taken from first principle simulations on smaller systems. And despite everything has already implemented, I have to say that in this work, we play only with the lattice part. So all our systems are insulating, and therefore, we are not using the electronic capabilities in this study. So we can do now several things using this second principles technology on these lead titanate, strontium titanate superlattices, such as the emergence of chirality in these polar vortex superlattices or the coexistence of phases of Pavel skyrmions. So due to time constraints, I will focus only in this talk in this first part. So if you are willing to get more information, we can discuss the other two at the coffee break. So we have carried out second principle simulations on lead titanate, strontium titanate with 10 unit cells of each. And here you have some of the results we are getting. So here the arrows point the components of the polarization in the plane of the screen, and the colors are the component of the polarization perpendicular to the plane of the screen. So green pointing inwards, magenta pointing towards you. So we could identify different atomic geometries that were very close in energy. In particular, the three that I am plotting here are degenerated in energy. So we do observe a continuous rotation of the local dipoles with pairs of clockwise and counterclockwise rotations as before, but superimposed to this structure, we were able to detect a component of the polarization pointing in the perpendicular direction of the screen, so in the direction of the axis of the vortices. So the fact that we have this component of the polarization here at the domain walls suggests that the domain walls themselves are ferroelectric. And this is a result that has been previously obtained, for instance, by Jacek Gordel and Jorge Iñiguez in 180-degree domains in bulk lead titanate. So they were able to observe that the domain walls themselves were able to sustain a component of polarization. Also, there was detected by the group of Klinka, where they were able to detect a very rich structure phase diagram predicted in these 111 barium titanate domains, and many works by Salge. So it's very well established now that the domain walls themselves may be ferroelectric. So here, the domain walls show a mixed easing, so the polarization going from up to down, mixed with null, so this rotation of the polarization in the plane of the screen, combined also with some block components where the polarization is just going out of the screen and coming back to it. So it's a mixture of the three of them. And the fact that we have also this axial component of the polarization makes the structures chiral. So we can take, for instance, one of them here, and this is the original one, the one that is here surrounded by this orange square here, and we can see how, and we are taking three reflections, three mirror reflections. One is this, another one is this, and another one is this. So we can see how the reflected images all map onto the other, but we cannot map any of the reflected images into the original one, just doing rotations or translations. So the structures with this axial component of the polarizations are chiral. And we can define a hand for all of them. So to do this, just take your right hand and then curl the fingers in the direction of the arrows. And then if your thumb is pointing in the same direction as the axial component, then the vortex is right-handed. If not, it's left-handed. So making this trick, we can see how the two vortices here are right-handed, the two vortices here are left-handed, and here in the middle I have one that is left and another one that is right. So we can say that we have here two structures that are chiral enantiomers, this one and this one, while the center one is achiral. So just to put some math on this, we can define the helicity. And the helicity is defined as the integral over the whole volume of the dot product of the local polarization times the curl of the polarization here. So since this polarization tends to measure the rotation of the dipole, we expect that the helicity density, the integrand of this, will be localized at the position of the vortices. So just taking this equation and computing it at the helicity density, we can see how the here the right-hand structure displays a positive helicity, the left-handed displays a negative helicity, while the achiral structure has a helicity that vanishes, essentially. So in the last couple of minutes, so that's the theoretical predictions. The fingerprint for chirality is would be that a different answer, a different reaction of the system under different circularly polarized light, left or right-handed. And this was precisely the experiment that was carried out in the group of Professor Rames at the University of Berkeley, where they were using soft X-ray diffraction. So soft X-ray, because of three reasons. First, the wavelength of the soft X-ray is well matched with the periodicity of the vortex, anti-vortex, or clockwise, counterclockwise vortices. The energy of the soft X-ray is very well matched with this resonant transition between the titanium 2P and the titanium 3D. So we can directly probe the anisotropic electronic structure of the titanium 06 octahedra, and we enhance the scattering cross-section. So essentially here, what we have is, okay, those are the typical spots obtained from the XRD experiment. And if we look at one of these spots, and we look at them in detail, we can detect the presence of satellites here that are the signature of a superlattice, of a superstructure with the clockwise, counterclockwise vortices. And if we perform here a cut, a horizontal cut, and plot the intensity of the diffract X-rays, we can see two things. First, the appearance of the satellites with lateral periods that matches very well with the counter-rotated vortex pairs. But second, that the intensity of the diffraction peaks are markedly different for circularly polarized incoming X-rays with opposite left and right-handed helicity, with differences that may be up to 20%. So this is a clear indication of X-ray circular dichroism that is the fingerprint for chirality in the system. So just the last slide. So the origin for this chirality can be traced back to the presence of a helical structure here at the center of the clockwise, counterclockwise vortices. So if we just plot a line here and look at how the polarization is changing, we can see how we have an helical structure. So the diffracted beams with a positive lateral component of Q sends a clockwise or counterclockwise helical rotation of the polarization, and therefore interacts much better with the left-handed polarized light, while the Q lateral positive sends a clockwise helical rotation of the polarization, so they interact much better with the right-handed polarization. So essentially, this is the take-home message. I think I ran out of time, so I leave the take-home message here, and I'm ready to take your questions. Thank you.
We have time for some questions. Okay. Microphone, please.
Could you please show the diffraction patterns a few slides ago, just towards the end?
This one?
And the next one was electron diffraction. Okay.
This or this?
Okay. Oh, thank you.
Anything else? So I have a question. It seems that the nature of the domain walls matters a lot in terms of whether you can have an Ising-like or a nail-like or a block-like wall and the mixture of those to get a vortex state. So is this general for a tetragonal ferroelectric, or can this live in a rhombohedral ferroelectric or orthorhombic ferroelectric where you might have more possible domain states to relax into?
Yeah, I think my experience is that the structure should have a tendency to show, well, of course, polarization up-down, but also to show the tendency for a polarization rotation. So in this particular sense, systems with a polarization along the 1-1-1 direction would be very good candidates to show the emergence of the three components at the domain wall. You have up, down, but then at the same time you have to go out of the plane of the screen, entering again, and for that it's very likely that if you have a system that shows somehow a tendency to have already a polarization along the three directions, that would be perfect.
Next, oh, one more?
Yes, thank you. Hi, I really enjoyed your talk. I think you made the argument that these flux closure domains and vortices are related to the length scale of heterostructure patterning in materials. What is the current status in your mind of the quest for finding vortices in materials where the underlying atomic and compositional structure is bulk?
And can we have the next speaker comment too, please?
Yes. If you have no compositional layering or no thin film behavior, will it also be possible to find vortex states, or is it required to have spatial confinement to have vortices?
No, it's not required to have a different. It's not required to have a different compositions in the system. In particular, we have some preliminary results on lead titanate, pure lead titanate, no related with strontium titanate, where you can induce locally a domain pointing down inside a matrix pointing up, and it's, let's say, automatically the system displays one skirmion-like structure. I mean, just the system wants to close the up-down domains, just forming this kind of closing pattern, and this is just for a single material, no need for two different materials. Of course, this will be metastable, because if you have lead titanate, whoop, everything will tend to polarize in a given direction. But at least you can stabilize them at a metastable level.
I think with that we have to move on for interest of time, but we can talk in the coffee break. So thank you very much. So our next speaker is Zustang Liu, who's going to talk about tunable inversion symmetry to control indirect to direct band gap transitions. Do you have an HDMI? You're right. Or there. HDMI.
Hello everyone, I'm Xuezheng Lu from Northwestern University. Today I'm going to talk about the tunable inversion symmetry to control the indirect to direct band gap transitions. Before the talk, I first thank the organizer for providing this opportunity with me. to introduce my work here. And I also thank my advisor, Professor James Rondinelli, for the instruction in the work. And this work was also supported from the Center for Nanoscale Science. In this presentation, I will first introduce an unusual polar to nonpolar transition in layered oxide by string engineering. And then I will mainly talk about our findings in the one-by-one ultra-short superlattices. That is, there is a competing nonpolar phase under epitaxial string, and also the indirect to direct bandgap transition in the across the transition as shown in the figure below. In calcium titanate 327 layered oxide, the polar to nonpolar transition in either compressive or tensile string was predicted, and which is featured by the changing pattern of out-of-phase oxygen octahedral rotation, in which the in-phase rotation in polar phase is transformed to the out-of-phase rotation in the nonpolar phase. But as studied by the Landau model shown here, we found that the string tunable trilinear related couplings in the two phases can be responsible for the appearance of the nonpolar phase under epitaxial string. To apply our theory to other compounds in the AB0327 family, we find more materials showing such unusual polar to nonpolar transition under epitaxial string. From this table, we found with small tolerance factor, the polar to nonpolar transition can occur in both compressive and tensile string. But with increasing the tolerance factor, only the compressive string can trigger the polar to nonpolar transition. And we also found that the polar to nonpolar transition can only occur in a range of tolerance factor as shown here. And it's very exciting that the PBCN phase in the bulk strontium zirconium oxide has recently been found at high temperature in experiment, which is consistent with our prediction on the temperature dependent of the stability of this PBCN phase. To further apply our theory and elucidate the general feature of a nonpolar phase in hybrid improper ferroelectrics, we just focus on this one-by-one ultra-short superlattices, which is predicted to be the hybrid improper ferroelectrics if the PMMA phase of each component can have lower energy. And this work was also concisely discussed yesterday by Professor James Rondinelli. And the work here is based on the density functional theory calculation coded in the West, where the PBE saw a change correlation functional is adopted in the calculation. And the way to apply the tensile and compressive string constraints is shown in the figure. And here we applied the in-plane backcell string. And we also use a genetic algorithm structure method to confirm the ground state structure under epitaxial string. And Landau model and Tedbany model are used to explain the phase transition and also the electronic structures in each structure. We then found in the lanthanum yttrium gallium oxide the previously predicted bulk PMC21 phase cannot be stabilized under backcell string, while the P21M nonpolar phase can be more stable in the whole string range studied here. And we also found in the lanthanum yttrium aluminum oxide the P21M phase can also be stabilized up to a tensile string at 2%. And to further elucidate the stability of the P2M phase under back-cell strain. We also investigated phase stability under the anisotropic influence strain. Here we found with increasing the AORB ratio, the energy of PMC2M gradually goes up, and the energy of P2M will gradually go down, which results in crossover at AORB approximately equal to 1. We then use the Landau model to explain the macroscopic mechanism on the phase transition. Here in the polar phase, there are 3 modes. One is the polar gamma-5 minus mode, and the in-phase rotational mode. The M2 plus in-phase rotational mode, and the M5 minus out-of-phase tilt mode. And in the non-polar phase, there are 7 modes. There are 7 modes. There are 4 anti-ferroelectric mode, and M4 minus out-of-phase rotational mode, and also the M5 minus tilt mode, and also the X1 plus tilt mode. And in the Landau model, we have 3. We have 3 parts. The first, which the terms only consist of the polar or antipolar mode, and the terms only consist of the tilt and rotational mode, and the last term only consists of the interactions between the first 2 parts. And the mode, the figure just describing the mode displacement. By comparing the phase diagram from the direct DFT calculation and also the Landau model, we found that this shows the similar tendency of the phase stability, but there is no difference here. We found that the phase transition occurs at 2% tensile strain, versus no transition occur in this DFT phase diagram. This discrepancy, this quantitative discrepancy is caused by the ignorance of the gamma 1 plus mode in the polar phase, and also the gamma 1 plus and X3 plus mode in the non-polar phase, which will not influence the main, the qualitative mechanism on the phase transition is brought here. We then decompose the energy of PMC2 and the P2M into the 3 parts described in the last slide, and then we find the energy difference between the anti-ferroelectric mode and the polar mode just increased, and the energy difference between the P2M and the PMC2M phases in the tilt and rotational mode just decreased. The total effects lead to the energy difference between the 2 phases decreased, which means the P2M phase should be stable under tensile strain. But this is in contrast to the results from the two figures. And by checking the energy difference between the 2 phases in the in the anharmonic interactive term, we found it's the strain tunable anharmonic interactive terms. Responsible for the compensate the energy difference between the first 2 parts in the 2 phases, and also lead to the correct phase diagram obtained from the 2 figures. And this mechanism is also applied to the phase transition under the anisotropic strain. And then we studied the electronic band structure in the 2 phases. Interestingly, we found the indirect band gap in this polar phase, but direct band gap in the non-polar phase. And before studying the electronic properties, we at first guess, we expect the valence band edge consists of the p orbital of oxygen because the d orbital, the d shell is closed in gallium, and also we expect the interband interaction between A cation and oxygen, between B cation and oxygen, also may also have effects on the valence band edge, which is verified by the density of states. And here, except the PP orbital interaction, the px orbital interaction, here X means the F and D orbitals, are also important to the formation of the valence band edge. Here we focus on the valence band edge because the CBM is always located at gamma point. And to study the band gap character changes changing between the two phases, we rely on the Ted-Bandy model. Here, in which the block function can be expressed in terms of the atomic orbital function, and then an electronic function can be a linear combination of the block function, and then we can finally obtain this energy band for this energy for each band at key point can be expressed in as this occurrence rate. And in occurrence rate, the matrix is inside of 148 by 148 and includes orbital interactions among the lanthanum d and f orbitals, yttrium d orbitals, and gallium s orbitals, and oxygen p orbitals in this 40-atom structure. And the Van-Neuronati calculation will carry out to obtain the orbital interactions in this matrix. And we then decompose the energy differences between the S and gamma point in the band structural polar phase, and also the ED and the energy difference between ED and gamma point in the nonpolar in the band structural nonpolar phase into the PP contribution and also the PX contribution. Then we found the PP contribution can be positive and the PX contribution can be positive and the PP contribution can be negative. We also found in the polar phase the PP contribution dominates, and in the nonpolar phase in the polar phase the PX contribution dominates, and in the nonpolar phase the PX, the PP contribution dominates, which just leading to the indirect band gap in the nonpolar phase and the direct band gap in the nonpolar phase. And we also, is there any okay. We also studied the mode effects on the on the band structure, on the energy differences between the S and gamma point in the polar phase, and also the ED, also the energy difference between the ED and the gamma point in the nonpolar phase. And the main conclusion here is the larger oxygen octahedral rotation mode in the equilibrium structure will favor the indirect band gap in the superlattice. I want to start it. This is okay. And we here we just obtained the I just talk about the conclusion and no discussion. And here conclusion is the tilt and the rotation controls will compete with the lattice parameter change. By we studied many materials in the polar phase with substitution of different A-side cation or the B-side cations to obtain this conclusion. So if you want to obtain and we finally obtained the increasing the tilt and rotation and also decreasing the lattice parameter, it will favor the indirect band gap in the polar phase. And this is the the design rule we just obtained by collecting the result from the material we studied here. And this is the conclusion.
Or maybe one or two short questions? No. With that, I think we're time limited here. So we bring the next speaker up, please. Thanks.
Thank you.
Our next speaker is going to be Raman Vasavedran, who's going to talk about emergence of mixed electrochemical ferroelectric states, piecing together a ferrionics picture of ferroelectric surfaces.
Good? Okay. Thank you, Mr. Chairman. I realize that me and my 81 slides are what is in the way between you and coffee, and I see a lot of tired faces after this is the third day. So I will try and keep it brief and just give you the gist of what we've been doing over the last 3 years or so at the Center for Nanophase Material Sciences at Oak Ridge National Laboratory. I should mention that this is not my primary work. I'm more or less kind of only tangentially related to this work. If you have some very technical questions and I can't answer them, I can certainly ask the right people if I'm unable to answer them. So I do apologize in advance. So we've seen a number of talks today about interfaces of ferroelectrics. And I think that, of course, that's very important. But one of the areas of ferroelectrics that hasn't received the attention that I feel that it can deserve is the bare surface of a ferroelectric, because a number of quite interesting processes can happen on ferroelectric surfaces, and particularly when you start to scale down your ferroelectrics to thin films, for example, of the 10 nanometers or so, the surface electrochemical processes can actually have a very large impact on the ferroelectric phase stability, and that's what we're really looking at in this particular study. So before I start, just the people who are involved with this work, of course, Sergey Kalinin kind of led it for the last 3-4 years at CNMS at Oak Ridge. But I really want to acknowledge Yi Kao, who is our postdoc, who is now at UT Arlington, as well as Anna Morozovska, who developed all of the Landau theory. And I think she's made some tremendous strides over the last 15 years in Landau theory of ferroelectric materials. Also, so many of our collaborators, both in ORNL and outside, as well as the US Department of Energy for funding this work. So, there's quite a number of papers now on this particular topic of this mixed electrochemical ferroelectric state. They kind of came out in the last, 18 months. And so I'm just showing probably the main ones here. I'm happy to send them to you in case you're interested in reading them. This is not a new idea per se. Of course, everybody knows the coupling between chemistry and physics in terms of ferroelectrics. It's quite important in complex oxides in general. Basically, if you want to understand ferroelectrics, you could draw these simple diagrams which are based on physics, so you have these autoparameters and the external stresses that can modify these autoparameters. But if you really want to understand them in real devices and in real materials, you also have to consider the chemistry and the defect chemistry. So for example, you have to modify this diagram by incorporating the electrochemical potential mu, because in general, when you apply electric fields, it's not just the polarization that can change, but you can move defects, you can move oxygen vacancies, and so forth. And so if you want to have an understanding of ferroelectrics, you really also want to have a good understanding of how you're changing the material chemically by applying electric fields and stresses and things. One of the major things, that has been kind of, I would say, it's been appreciated in literature, but more or less people have not thought about it that much, and that is that polarization, in order for it to be stable, obviously requires screening, right? So if you have a ferroelectric surface, you don't have screening, then what's going to happen? So generally, if you're in ambient conditions, you're going to have species that can screen the polarization. In the absence of that, what will happen is the surface is going to somehow reconstruct, because the bulk obviously wants to stay ferroelectric. So if the bulk is quite large, the energies are going to be quite large, and the surface really has to follow the bulk. And so we've, over the last 2 decades or so, have a number of experiments from Kelvin probe force microscopy to try to understand surface charge dynamics in ferroelectric thin films and ferroelectric single crystals. And so you can see some quite interesting results that have been shown. For example, you can see that you can take barium titanate or other materials above their TC, and you can see how the surface charges kind of invert. You can see shadows after a moving domain wall. You can also see some very interesting features when you try to switch ferroelectrics locally. For example, in this lithium niobate study, which was published in Nature Physics by Anton Ivlev and co-workers, you can see they have this kind of almost quasi-periodic structure. Some interesting domain shapes can show up, and some even chaotic domain switching can occur. And all of these really require you to understand ionic screening processes on the surface. So if you want to switch the polarization, you actually have to take into account screening for this to occur. One of the greatest, I would say, one of the really good works in the last decade in ferroelectrics has to be coming out of Argonne in this particular work by Hyland and Stevenson. And what they did was they took an ultra-thin ferroelectric film, lead titanate, I think it was less than 5 nanometers or so. And what they did was they put it into a chamber and they changed the partial pressure of oxygen, at slightly higher temperatures. And what you clearly see is that by simply changing the partial pressure of oxygen, they're able to induce ferroelectric switching. So you see this nice butterfly hysteresis. So without applying any electric fields, they're able to switch their polarization. So this obviously has something to do with screening on the surface. And so they did some calculations, and so they did the initial thermodynamic treatment. And what they found was, for this particular thickness of lead titanate, there are different states of polarization that are preferred under different partial pressures of oxygen, right? So this is exactly what they saw in experiment. This is also relevant, for example, for so-called charge collection microscopy, and so I can point to a review. That's kind of work that's, again, happened from Argonne and Sungbom Hong, who's now at Korea. There is also some first principles calculations on ferroelectric surfaces. So for example, you can see that depending on the polarization orientation in your ferroelectric, you'll have different types of surfaces, and different types of surfaces will be stable. So you'll have different reconstructions. So I'll just point you to one work here with lithium niobate. And so obviously you have this kind of very complicated phase diagram depending on your electrochemical potentials involved. But the gist of it is basically that if you don't have screening from external charges, your surface should reconstruct. And this reconstruction is going to depend on the polarization orientation, obviously. And so that's kind of what's shown in these two studies, in this case for lithium niobate, in this case for lead titanate. So if you look at bulk ferroelectrics, you can pretty much write Landau expansions, and you can pretty much predict properties pretty well with current Landau theory. And so you can go ahead and add these terms. And in general, you don't have to worry about the surface so much because, as I said before, the bulk polarization energy is so much higher that the surface really has to follow whatever the bulk does. And so it's not so important when you're looking at single crystals to be able to look at these effects. But we're in the thin film session, and of course, when you go to 30 nanometers or thinner, what we find is that the surface electrochemical processes become on the order of the same energy scales as the bulk polarization energy, and so you have some very nice mixed states that form, which I'll get into in the next few slides. So how do we actually try to model this? So we take our standard ferroelectric equation of state, which is kind of shown here, right? So this is just the standard ferroelectric equation state, and we don't do anything to it. We don't add any terms to it. All we do is we change the boundary condition. So the boundary condition now is, instead of the electronic screening boundary condition, you have a chemical boundary condition. And so that's kind of given by this surface charge density here. It depends on the applied potential, which obviously has to be solved self-consistently. It depends on the charge of the ion and the area of the ion. And it kind of follows, we say that it follows an absorption isotherm. So what this means is that the surface charge density is going to depend on your pressure of oxygen in the chamber, for example, as well as this delta G value, which is the energy of formation of a surface ion or defect. And so you can think of this here, that this is the surface charge. As you change the pressure, you're going to change the surface charge density, right? So Anna went ahead and calculated what it should look like for barium titanate under different thicknesses. So in the case here, you can see the phase diagram for barium titanate under ideal screening, right? So this is the general case, which everybody already knows. You have at high temperatures, oh, it's a bit hard to see. So at high temperatures, of course, you see that it's paraelectric, there's no polarization. As you go to lower temperatures, of course, you start to have two polarization states which are equal in energy, so it's entirely symmetric. And there's nothing very interesting happening here. This is what everybody has seen from 40, 50 years ago at least. You can also introduce a dielectric dead layer. This is basically just a finite thickness over which the potential will drop to the external applied potential. It doesn't change the calculations at all. Basically, you have a slightly reduced polarization, but there's nothing qualitatively different about these two cases. But now let's look at the more interesting case where we have this electrochemical boundary condition. And so you can see this here. At high temperature, of course, it's paraelectric. You see nothing. At low temperature, you see in this case there is a polarization that's stable here, and there's a polarization stable here, so that checks out. But in this intermediate range between 200 and 600 Kelvin, you can see that there's a large region where there's only one stable polarization state. So this is what we call the mixed electrochemical ferroelectric state, and the reason, or the so-called ferroionic state, and the reason we call it this is because in this case, the stability of the ferroelectric phase is more or less determined by the surface ionic species that are present. So depending on this value of delta G, you're going to get slightly different polarizations, right? And that's in fact what you would expect if you have a mixed electrochemical boundary condition. Also, if you want to make sure that this is self-consistent, you can do this as a function of thickness, and what you find here is that for thinner films, your region of this mixed state is very large. As you go thicker and thicker, the surface becomes less important, and you find that this width of this mixed region is actually rather small. So this kind of agrees, it's kind of a sanity check almost. But it's a little bit hard for us to, physically change these delta G values. Of course, you can't do that because it's kind of given by nature. What you can do is apply voltage. And so apply a potential. Let's see how these phase diagrams change under applied potentials. So in this case, again, ideal screening, what do? You simply asymmetrize a double wall potential, and you'll stabilize one polarization state over the other. And that's exactly what you see in the ideal screening case. You see that here, when you apply a slight potential, one of this state is favored over this particular state. So that's why there's an asymmetrization in this diagram. And the same thing happens when you also consider this dielectric dead layer. But what happens now when we want to try to apply potential for this particular state here? That's the more interesting case. And so I'm going to explain to you what happens here. And it's quite interesting. So if we start with a 3 nanometer film, you will see that in fact at 3 nanometers, there's only one polarization state that's stable, and it's only at very low temperatures. But by applying potentials, you're able to stabilize all different types of polarization states here. So I wish this... the color, I guess, of the laser is bad. It's kind of blending in with this. But in any case, you can see that you can kind of access a range of polarizations by applying potential in this case. Similarly, you can do that for a 30 nanometer film, where now we've kind of recovered the ferroelectricity here. And then for really thick films, it's almost back to the standard bulk ferroelectric type behaviors. And so you can think of this more in a schematic level, where if you have a very, very thin film, you kind of lose this, you lose the two states of polarization. And as you go thicker, you start to gain them, and they kind of become more well separated. You can go ahead and calculate what these phase diagrams should look like. So this is an example where Anna has calculated the phase diagram for 20 nanometers, 100 nanometers, and 300 nanometers of barium titanate. You can see that this is as a function of temperature and pressure. This MFE is a so-called mixed ferroelectric state. You can see that this mixed ferroelectric state becomes less and less important as you go to thicker films, as you would expect. Interestingly, there's also this kind of strange critical points that exist in these phase diagrams. One of the, I would say, interesting finds from piezo response force microscopy studies in maybe the last decade or so is that it seems that you can possibly, I should say, because PFM has a lot of artifacts, obtain a range of polarizations for in ultra-thin films. And so the question is, what is the origin of these types of effects? One of the possible origins is explained by this particular theory. So if you look at this particular diagram, this is a 30 nanometer, in this case a 30 nanometer film. If I change the partial pressure of oxygen, I'm going to change the polarization at a given temperature, and the same thing would apply for fields. And so it's possible that by incorporating this changed boundary condition, we can start to explain some anomalous features that we've seen in local experiments with piezo response force microscopy. How can we possibly identify some of these states? So for that, we turn to a technique called contact Kelvin probe force microscopy. This is basically where you take hysteresis loops, but instead of taking a hysteresis loop and reading the piezo response at 0 volts, we now read the piezo response at different voltages. So in this case, -2, -1, 0, 1, and 2. You can forget about this BE packet here. This is just a read packet. So basically, this is what's applied, and so you're kind of reading the signal at different voltages. And so what we hope to do by this technique is to be able to look at the dispersion in the polarization states as a function of these DC voltages. So if we take a standard material like strontium titanate and a thin film on dysprosium scanner, this should not be ferroelectric. And indeed, when we look at this response, you can see all straight lines, which suggests that this is purely electrostatic response. But let me walk you through what this diagram actually means. So this here in the bottom axis, in the x-axis, is the read voltage, or that's those offsets that I showed you before. So basically they come from these offsets, and so each one of these points comes from these offsets at a particular write voltage, which is given by the color. So if you go along this line, it actually tells you the surface potential after applying some voltage. So in this case, after we apply this minus 15 volts, of course this red line here, you can read the surface bias, which is around minus 2.7 volts. Similarly, you can do that on the positive side. So after applying plus 15 volts, you see that the surface bias is something like 2.8 volts. Why is this important? Well, if you look along this particular axis here, you will see some bunching, right? So you see some lines bunching here and some lines bunching here. And so even from a purely electrostatic response, you see this kind of hysteresis loop that occurs. And this is interesting and also kind of disheartening in a way, because this means that if you see this ferroelectric hysteresis loop in PFM, it doesn't mean that you have a ferroelectric material. Nonetheless, the important part here is that I want to give you an idea of how to read these particular diagrams. We also think that the reason why you see this kind of bunching is because what you're doing is you're creating some dipoles, for example, either within the material or within the tip surface junction, and that's actually responsible for this type of hysteresis. So we wanted to try to see if we could measure this kind of dispersion in the polarization in the ferroelectric states. And to do so, we were very lucky to collaborate with Catherine Duberdu, who is now in Berlin. And so what we found was that she grew some barium titanate on silicon, and we found that when we do these CCAP-PFM studies, this STO on silicon. You can see it's pretty much flat. There's hardly any dispersion. In the 10 monolayer case, you can see one polarization state here and another polarization state here, and the width of this kind of reduces as you make your barium titanate smaller, so thinner. So this is the 10 monolayer case, 7 monolayer case, and 4 monolayer case. But still, you can see that there's a switchable polarization at 0 volts. It's kind of interesting. We've also done some phase field modeling on these particular states, and so you can clearly reproduce chemical hysteresis loops through the phase field method when you incorporate these different boundary conditions. So I kind of point you to this particular paper it was in PhysRev B by Yi Kao very recently. So in summary, I think ferroelectric surfaces can be quite interesting. I think they can obviously have some very important impact on the ferroelectric phase stability when you go to ultra-thin films. And in order for us to understand this better, we need chemical imaging tools, and we need more atomically resolved studies of ferroelectric surfaces in order for this to be kind of taken to the next level and really give us a nice understanding of the couplings between surface and bulk processes in thin film ferroelectrics. So with that, thank you for your time.
For a few questions before the break here. Go ahead.
Would like to ask about the film strontium titanate on dysprosium scandate. So you claim that the polarization hysteresis loop is just artificial in this case, but you measure polarization out of plane of the film.
Yes.
But in this case, the strain is tensile and the polarization should be in the plane. So can you comment it? It should be polarization in the plane there. There is also dielectric anomaly in the plane and not out of plane.
So as far as I know, its strain is quite small on dysprosium scantinate.
1%.
Right.
It's
okay. Well, whenever we do the lateral PFM studies, we're unable to find any signal that would suggest an in-plane polarization, is all I can say. Yes.
So could you measure as well in-plane polarization?
Well, we can measure the in-plane strain, yes. If it exists, we can do it, yes.
Okay.
Yes.
Thank you.
I just want to ask, I guess, kind of obvious question about timescales in kinetics. I mean, at what timescale does a screening occur? I guess it will depend upon what kind of system, but can you give us some idea of the orders of magnitude?
Yeah, this is a great question. So our time-resolved Kelvin probe force microscopy experiments suggest that there can be some really fast processes that occur and some rather slow ones. So, it might be on the order of seconds for long, so you could take, for example, lateral electrodes, bias them, and see the transport of charged species from Kelvin probe force microscopy studies, and they clearly show slower timescales. But in general, if there are faster processes, and I assume that there are both fast and slow processes here, our KPFM studies can only go down to, let's say, a few tens of microseconds. So if it's anything below that, at a really local scale, we won't be able to measure it, not with our existing techniques.
With that, go ahead.
Thank you for the talk. You have shown these ferroelectric loops that are not in fact ferroelectric. Is there a way of making a criterion which says, okay, this is ferroelectric and this is fake?
So that's a really good question, and we've written a very long review article on that topic, so I'm happy to send it to you. It was very painful. But basically, what I'm willing to say here is that we know what a true ferroelectric looks like in the CKPFM experiment. So when I say true ferroelectric, when the polarization is very large, so PCT, barium titanate, lithium niobate, we can see a clear dispersion. So we can clearly see the distinction between this type of CKPFM result and what we got in the STO. On a more fundamental level, I cannot claim that just because it does not show this type of behavior in this experiment that material is not ferroelectric. And the reason for that is because, number one, there's a noise problem. So if your polarization is less than 2 microcoulombs per centimeter square, you're not going to be able to see it. It's just that's the noise limit for our technique. The second problem is, of course, that there's obviously a lot of surface problems. So PFM is surface sensitive, and so if you have some kind of dead layer at the surface, or you can't switch the polarization at the surface, like happens in relaxers, for example, then you might come away from this thinking that all you have is electrostatic response, and you don't have a switchable dipole. But that's not actually obviously the case, because you're more interested in the bulk polarization and whether you can switch the bulk microscopic polarization. And so for that, I think what we really need is you need to combine experiments from complementary methods to try to see what is ferroelectric and what's not. I have a suggestion to try to make a decision tree-like approach, where we can talk about it.
Okay. With that, I think we'll thank all the speakers again. It's time for a break.